All right, let's look at solving a couple of problems using our ideal op amp assumptions. Here's a first problem let's look at. Notice first of all we see that it's not one of our normal inverting or non-inverting configurations, so we're just going to have to use the assumptions. And our second one is the same thing. It's not inverting or non-inverting. We've got something odd going on in here, so we'll have to work at using our assumptions. All right, let's see how that goes. So one of our assumptions is that there's infinite gain in here, and that there is a feedback loop from the output to the inverting input. We see there's a connection there. So a voltage change here will have an impact at this point. And we'll assume it's in the linear range, so that whatever voltage I have here at the non-inverting input, we'll call it V1, I will also have that same voltage at the inverting input. Let's call that V2. So we're going to assume right off the bat that V2 is equal to V1, whatever that is. Now in this case, we know V1 because V1 is connected to this power supply. We know it's 4 volts. So we now know that V2 is equal to 4 volts, right? If I have 4 volts here, I must have 4 volts here. Okay, we can't do one of our handy-dandy formulas, but we can do a Kirchhoff's current law at this node right here. Oh, the other thing is, how much current is going to go into that lead? That's going to be 0. I is equal to 0. It's a tiny little I and a tiny little 0. There we go. But anyways, no current going in here. So whatever current we have coming up here, and that's 1 milliamp, we know that that can't go in here, so it must all go up here. Therefore, we have 2 milliamps up here. Excuse me, not 2 milliamps, 1 milliamp. All right, so let's do a Kirchhoff's current law at node 2. What does that give us? The current in, 1 milliamp, is equal to the current out, which we know is 1 milliamp, but it's also V2, it's a drop in voltage over the resistance. So it'd be V2 minus V out over 2K ohms. Well, now wait a minute, we know V2 is 4 volts. So we now have that 1 milliamp is 4 minus V0 over 2K ohms. If we solve that for VO, solving that for VO, we get that VO is equal to 2 volts. Just doing a little algebra on that guy. So there's our approach. You can see how the assumptions worked for us in this case. Let's look at this second guy here. Let's see, whoops, I forgot to put something on there. This is a 1 volt supply here, all right? Uno volts. All right, so once again, we have some negative feedback. There's a wire connecting the output of the op amp that's going back in the inverting input, so that's good. So our assumptions work. Whatever my voltage is here, I'll have the same voltage here. Okay, there's no difference in voltage between these two, because if they were, the output would go as far as it needed to make that be the case. So we know that V2 is equal to V1. Now V1 we know because it's hooked up to a power supply to ground, so we have ground. We're going up 3 volts. So V2 is V1, which is also 3 volts. All right. Now we just need to figure out what V out is relative to the 3 volts I have right there. Well, notice I have some voltage at V out, and it gets bigger before it gets to V2. So V2 is bigger than V1 then V out, excuse me, by how much? 1 volt. Right, everybody see that? Whatever voltage I have right here, it gets increased here by 1 volt to get V2. So, as it turns out, V out is equal to, V2 is equal to V out plus 1, or V2, we all know is 3 volts, is equal to V out plus 1. So V out is equal to 2 volts. There we go. There's a couple of little problems using those op-amp assumptions.